Welcome back. So, I hope you watched the last video because if you didn't, you're not going to be able to do this. You might remember I asked you in that video to go through the entire process of calculating the standard deviation for dataset 2 because in the video we did it for dataset 1. If you haven't done that, you'll want to pause the video and make sure that you can do that on your own before I give you my solution, because if you don't, you may never learn how it works, and that would be a shame. So, go ahead, pause the video, find your standard deviation for dataset 2, come back so we can check answers. Here's everything we need to calculate the standard deviation for this dataset. Step 1, your first column of this table, labeled X, it's just the data values that we started with. We calculate the mean, adding up all those values, which is 105, divided by the number of values we have, 15. We get a mean of 7. Then we calculate the second column, which is the original data values minus the mean that we just found. So for this first row, we're taking the first value, which is 0, and subtracting 7, the mean, to get negative 7. Doing that all the way down gives you these values here. And yes, just as promised, these numbers are slightly more interesting than what you got for dataset 1. At least we've got all different numbers here. And then for our third column, we're just taking the values in the second column and squaring them. So these negative values here become positive and squared, and then these are just those values squared as well. We add up all the numbers in this column. That should give you 280. Okay. To get the variance, we take that sum of 280 and divide by the sample size, 15 minus 1. So 280 over 14 gives us 20. That's the variance. But remember, the units on that are squared, so we take the square root as our final step. The square root of the variance, square root of 20, is about 4.472. That's our standard deviation. We interpret that standard deviation. The typical value in this data set is around 4.472 away from the mean. That's the best we can do for now for an interpretation of that number. So, hopefully you got that correct. If not, well, I mean, hopefully you can see where your work is different than this. I suppose it's possible that I made a mistake somewhere. I don't want to pretend that I'm perfect, but I'm pretty sure this is right. So you can see if each of these columns is the same. If not, where is it different? Maybe you left these negative and the sum was 0. That's a common mistake. Maybe you just copied something down wrong. It's possible, right? If you have questions on this, if you're still not getting it, let me know, shoot me an email. We can set up a Zoom meeting, or I can just answer over email. I want to make sure that you understand this process and you can calculate the standard deviation from any data set I give you, because that will be something that you'll be asked to do several times in the next few weeks. So, we can calculate the standard deviation. We're now pretty good at measuring measures of center and spread. But the interpretation here is still a little murky. So, like, what if all these values were, like, just bigger? What if we had a data set whose values were, like, in the thousands or tens of thousands? Like, if I wanted to know the annual incomes of the people in your neighborhood, right? Those values are not going to be these. They're going to be in, like, tens of thousands of dollars. Data sets with larger values tend to have larger standard deviations. So it becomes difficult to compare data sets that have very different scales, right? It'd be hard to compare a data set with these numbers to a data set with numbers in the tens of thousands, because those standard deviations, and the means also, would be so much different. It'd be nice if there were a way to compare. How big is this standard deviation relative to how big these numbers are? And that's going to be our last measure of spread that we will talk about. So in your notes, we've got this last term here. Sorry, nothing happened to you, but I saw something awful, a black screen. But it's back. The coefficient of variation, or CV, of a data set. This statistic will allow us to compare data sets that have vastly different numbers by putting them on the same scale. How is that possible? Well, let me show you. The coefficient of variation, which I will always refer to as the CV because I'm lazy and I don't like words very much. That's not true, I just like saying it. It's going to answer the question, how large is the standard deviation? I also tend to abbreviate standard deviation because those words are long. I'm just in a lazy mood today, huh? How large is the standard deviation compared to the mean? Okay. How spread out is this data set versus this one compared to essentially how big the numbers are in the first place? Right? Because bigger numbers are typically more spread out, but are they more spread out just because the numbers are bigger? That's what the CV is going to answer. So, again, this is useful because it allows us to compare data sets on different scales or even using different units. So, like SAT and ACT scores is a common set of variables that normally can't be compared because they're on different scales. The ACT, you can only get to like a 36, but the SAT, you can get up to a 1600. SAT scores are going to be higher than ACT scores. They're not going to be directly comparable based on their mean or their standard deviation. But with the CVs, we can compare those directly to answer that question for both of them. Let's talk about the formula. For a sample, it's going to have a different formula than it would for a population. That's similar to what we said for the mean. It's actually the same as the standard deviation, but we didn't talk about the formula for the population standard deviation. And there's a reason for that. It's because it's different, and I don't want to get into it yet. But for the CV, for a sample is going to be equal to, the standard deviation is denoted as just S for a sample. Okay, so it's just lowercase s. That's our notation for the standard deviation. It's just like the sample mean is x bar. The notation for standard deviation for a sample is s. For the variance, it's s squared. I probably should have said that in the last video. I forgot. Sorry about that. So when we use s in this formula, we're talking about the standard deviation for a sample. We're going to take the standard deviation and divide it by the sample mean, x bar. Standard deviation divided by mean. And we're going to multiply it by 100% because the coefficient of variation is always reported as a percentage. Always. Okay, so it's essentially what percent of the mean is the standard deviation. So, not a terribly difficult formula for a sample, and I would say virtually every time you calculate this, it's going to be a sample that you use. So you're going to be using this formula for the CV. For a population, the formula itself is the same. The only things that are going to change are the notation we use for the standard deviation and the mean. We would use their population parameter notation instead. The population standard deviation, that's really small, I don't know if you can see it. I'll blow it up a little bit here. This is lowercase sigma the Greek letter. And this is how we refer to a population standard deviation. Okay, so for a sample, we call it S. For a population, we call it sigma. Okay, so that's why for a population coefficient of variation, we're using sigma, because it's for a population. Okay? And we're going to divide it by not the sample mean, but the population mean, which I'm sure you remember the notation for that. It was mu, that Greek-looking M. Okay? This is for the population mean. And that also is multiplied by 100%. Okay? So we won't be using that one as much, or really ever. But it's important for you to know that to calculate the coefficient of variation, standard deviation divided by mean times 100%. Not too bad of a formula. Not super complicated. The most common mistake, people take the reciprocal, they put the mean on top and the standard deviation there. That's a no-no. Other people forget to multiply by 100 and they report it as a decimal. That's also bad. And make sure you refer to it as a percentage. Good. So, let's calculate the coefficient of variation for dataset 2, since it's right here. So the coefficient of variation for dataset 2. Okay, we're going to treat this as a sample, so we're going to be using this formula here. Coefficient of variation is going to be, I'll just go ahead and rewrite the formula, couldn't hurt. Let's see, S, the standard deviation is 4.472. We divide that by the sample mean, which we said was 7 down there, times 100%. And, I got my calculator handy today. 4.472 divided by 7 times 100. Okay, obviously this is 100% here, but on a calculator you would just type times 100. That gives you 63.89. The reason I put the percentage in the formula here is so you remember that this is a percentage. So for data set 2, the CV, the coefficient of variation, is 63.89%. What does that mean? How large is the standard deviation compared to the mean for this data set? The standard deviation is 63.89%. As large as the mean. That is the interpretation of your CV. It's how large the standard deviation is compared to the mean. So what about for data set 1 that we did in the last video? If I wanted you to calculate the CV for that data set, what information would you need? Because I don't have anything for data set 1 here. All you need, looking at the formula, if you want to find this, you only need the standard deviation and the mean. That's it. So for data set 1, CV equals, you'll find I'm a huge fan. Whenever I'm plugging numbers into a formula, I write the formula first. And that's because so many times in my life, I've made a mistake on problems like this just because I was rushing. I was going too quickly. And I messed something up that was silly. And I would get the graded quiz or test back or whatever and be like, oh my gosh, I can't believe I did that again. It happened over and over and over. I eventually was like, you know what, if I just write the formula first and then make sure I plug in everything I need, I can't make a mistake that way. So if you found that that's happened to you in the past, it really didn't take that long for me to write this. And it will absolutely prevent me from making a silly mistake. So, what were the standard deviation and the mean of data set 1? I won't make you go back to the last video. The mean was 7. And the standard deviation was 0.845. Okay, so if we do that, 0.845 divided by 7 times 100, I get 12.07%. Okay, so if I want to interpret that, the standard deviation is 12.07%, as large as the mean. Okay. Same interpretation, just a different value. Okay. Now, if you remember, data set 1 was just a bunch of 6s, 7s, and 8s. Those numbers are not very spread out. So we saw that compared to data set 2, all these numbers are a lot more spread out. Data set 2 has a much larger standard deviation than data set 1. Right? These numbers were much closer, so it had a smaller standard deviation. And since those data sets both had the same mean, but data set 1 has the smaller standard deviation, it also has the smaller CV, or coefficient of variation. Okay. Now, obviously, not every data set is going to have a mean of 7, so if that denominator changes, that will also affect the CV. But no matter what you get, as long as you use this formula and get your answer here, that is the interpretation of it. Yes, it's possible for the coefficient of variation to be over 100%. You could have a data set where the standard deviation is greater than the mean. It's possible. I wouldn't say it's particularly likely. That requires a certain type of data set, but it is possible. But the coefficient of variation can be negative. When would the coefficient of variation be a negative number? Looking at the formula. The standard deviation of a data set is never allowed to be negative. The smallest it can be is 0, and that's if all the numbers in the data set are the same. So it can't be negative because of the numerator. If the mean of the data set is negative, the CV will also be negative. Okay? So really, there's no limit on what the CV can be. It could be a ridiculously high percentage if your standard deviation is large but your mean is small. And if your mean is negative, coefficient of variation can be negative. Those probably won't be the case for any of the examples you do, because I would say most of the time it's going to be a percentage between 0 and 100. But I just want you to be aware, it doesn't mean it's wrong if it's something that looks wacky. It is possible that it can be some strange values. So that's it for section 2. In this section, you learned about how to calculate variance, standard deviation, and coefficient of variation. You should be able to calculate all of those measures of spread for any data set I give you. If you're asked to calculate variance and standard deviation, you'll go through this process. Once you've done that, you'll be able to calculate the CV, but you need the standard deviation to calculate the CV. It's possible I may give you some of these values and ask you for this. You should be able to plug in the relevant values there as well. It will actually be a while until the next video. You've got several things to work on before then. You've got a day to work on the homework in the textbook from this section. You've got a day to work on your project. You can now calculate these statistics for your 2 variables. You'll need a table for each one. You will have a quiz over the 2 sections that we've just covered in Chapter 3. All the measures of center, all the measures of spread. That might be it. No, because then you'll essentially be finishing your project before we even start the next section. you'll actually have several days next week to work on a scatter plot for your project, and I will actually give you a video on that. So you'll have a video for the scatter plot. I'll take you step by step exactly how to get that done. You'll have a day to work on your slideshow, and you'll have a day to work on just anything miscellaneous, anything that's been bugging you. If it takes you 2 days to put your slideshow together, whatever you need. All right. For these last 2 weeks before fall break, some of you are going to be in class right now, and some won't. You'll be in 2 days a week. So whenever you are in school, you can ask me during the class period that you've got me. I can help you out with your project. Perfectly happy to do that. That's what that time is for. If you are home on any given day, you can contact me, but I won't be available during school hours anymore, starting next week. So it might take me a little longer to get back to you if you're not at school that day. But the flip side, at least for those who are going to be attending, is you will get time in person to ask about your project if you need it. So lots of things to do, lots of things to work on. I will see you in the scatter plot project video. And until then, have a great day.